All right, here we go. Unit 1, Day 3. Today we're going to be talking about graphing functions with vertical, meaning up and down, and horizontal, meaning left and right transformations. I say transformations because we're going to be taking functions that we know what they look like an absolute value function, and we're going to be shifting them all around the coordinate plane. So maybe we're going to shift an absolute value function, looks like this v. Maybe we'll shift it up 5 and left 1. And we're going to use our knowledge of how transformations work to quickly graph and identify functions. First, we'll talk about vertical transformations. So if you have a function, f of x, and you write that same function, but then you write plus k on the outside, that's going to take whatever your function is, and it's going to shift it up k units. So every point just goes up that many spaces. If you have f of x minus k, you take your function, your parent function, and you shift everything down k units. Parent function, what I mean by that, is just like the baseline, like before you've done anything to it, like say the absolute value of x. So let's say we wanted to graph this quick, like the absolute value of -2. I know that comes out as +2, -1, the absolute value is +1, 0 becomes 0, 1 stays a 1, 2 stays a 2. And so we can use plugging in like that to help us graph if we've forgotten that it's a V-shaped graph. And I'm going to draw this as a dotted line. You'll see why in a second. A V-shaped graph that is centered at the origin, slope of 1 to the right, -1 to the left. If I take that function and I tack on, as we have here, +3, and this is important, on the outside, so on the outside of our function, what that's going to do is you do the f of x, the original f of x part, you take the absolute value, and then you just add 3 to the output, add 3 to the y value. So you take the absolute value of -2 to get 2, and then you add 3 to get 5. Take the absolute value of -1 to get 1, add 3 to get 4. Add 3 to 0, gives you 3. Add 3 to 1, you get 4, and so on. So we get this same shape. We get this like down and then up absolute value shape. Everything's just shifted. Instead of -2, 2, we're shifted up 3 spaces, -2, 5. Up 3 spaces to 1, 4. Up 3 spaces to 0, 3. So everything looks exactly the same. It's this exact same V shape. It has just been transformed vertically up 3 spaces. So it has been shifted up 3 spaces. That's a vertical transformation. What's really key here is that this is what happens when you add that 3 after the absolute value portion, not inside or during, but after. You do the absolute value first, then add 3. Because you do the absolute value, that gives you your V shape, then everything moves up 3. On the other hand, a horizontal transformation happens on the inside of your graph. And so if you have f of x plus h, notice that h is inside the parenthesis, so you do it to the x before you evaluate the f of x function. And we're going to see why in a second, but f of x plus h is actually going to shift our graph plus h. You would think to the right, but it's actually to the left 3 units. Whereas f of x minus h, that's what shifts us to the right h units. And I think a really easy way to think about this is to think about our normal absolute value function graphing techniques, where we said, okay, how do you graph the absolute value of x? You think about the vertex. You think about where does the absolute value turn around? The vertex is at 0, 0. Because when x is 0, the absolute value is 0. But if you went 1 in either direction, you're going to move up 1 space. So we use that technique, and the same idea applies. So where is the vertex of the absolute value of x plus 2? Where is that vertex going to be? And it's going to be at an x of -2, because it takes -2 in x to get that output of 0. And so if we were to go ahead and we were to fill out like an extended table, say we started at -4 and then we went all the way here, we'll see why in a second. If we were to just do our normal absolute values, that would give us 4, 3, 2, 1, 0. I've already graphed this, so just doing that quickly. If we do the absolute value of x plus 2, so now I'm taking these x values and I'm plugging them in here. -4 plus 2, -2, absolute value makes it +2. Notice that +2 occurs right here. So you actually have to go left 2 spaces to -4 to get that same output. So our first point here, if we're doing it this way, is -4, 2. Notice left 2 spaces. Now we'll do -3. -3 plus 2 is -1. Absolute value makes it +1. As predicted, left 2. There we go. The key here is to understand when x is -2, -2 plus 2 is 0. That's why our vertex is shifted left 2. -1 plus 2 is 1. Absolute value makes it +1. At this point, we can tell 0 plus 2 is 2. Our absolute value graph has started to turn around. So it's just going to continue upwards like that forever because we've made our turnaround. And as you can see, left 2 spaces, left 2 spaces, left 2 spaces. Everywhere you go, you're just going to be shifting this graph left 2 spaces from our parent function, the absolute value of x. We can put these two transformations together. For example, in the function, the absolute value of x -4, then -2. First thing always is to just remind yourself, because we're going to be working with different parent functions as well today. What parent function are we working with? We're working with the absolute value of x. So 0, 0, 1, 1, 2, 2, -1, 1, -2, 2. It's our standard absolute value graph. It takes all the x coordinates and it just makes them positive to get your y coordinates. That's what an absolute value does. And I'm going to write down our shifts. X -4. That's on the inside of the function, so it's our horizontal shift. And if you can't remember that -4 means to the right 4, think to yourself, where would the vertex be? It would be at +4. So instead of being at 0, we're going to go right 4 spaces to +4. But we're not going to stop there, because if we plug in 4, where's our vertex going to be? 4 -2. We still have to go down 2. And when we're working with absolute value, right, you can kind of see it's the same logic that I've been applying when we graph the absolute value functions. The vertex is at 4, -2. But not only is it at 4, -2, all you have to do to graph any point is go right 4 and down 2. Right 4 and down 2. There are 2 points to the right. We'll do this one now. Right 4, down 2. There's our next point. Right 4, down 2. You can see that you can graph these functions just by applying your understanding of transformations. So I want you to think about this next one on your own for a second. What if we had the absolute value of x plus 5 minus 3? I'll help you out by starting off with our parent function. We're still talking about our absolute value function. I don't want text. Our absolute value function. So everything you do is going to be based on taking a transformation of this dashed absolute value function with vertex at the origin that I've talked about. So I want you to think through the shifts, tell me what the shifts are, and then tell me what this new graph is going to look like. Okay, on the inside we have x plus 5. That is going to be a shift of left 5. So I'm going to start up here, I'm going to do dashed lines, left 5 spaces. Then -3, that's going to mean down 3 spaces. And the more practice with this, you'll get plenty of practice with this, the better you're going to get. There is our new vertex. You can either keep drawing those points, left 5, down 3, left 5, down 3, or you can just look at this and say, okay, it's going to go up 1, over 1 in both directions. To the right, we have that slope of 1, so it's like it's 2 functions. To the right, we have a slope of 1. To the left, we have a slope of -1. It makes that V shape. This green graph is the graph of the absolute value of x plus 5, then -3. Now, we've been working with absolute value functions for 2 days. I like to start with absolute value functions because by having you first learn to think about this through the vertex, you kind of start to intuitively see how these shifts happen, and specifically why +5 means x has to be at -5 at the vertex. why that makes a left 5 shift and then down 3. But this works for all kinds of functions that we're going to be working with a lot in Algebra 2. We're going to run through these quickly today because they come up in the Delta Math, but don't worry, we'll get a lot more practice with them. First, the quadratic function. You've seen this in Algebra 1. It takes the input and it squares it. It multiplies it by itself. So I'll redraw these dots here as they come up. Negative 2 squared, meaning times itself, is positive 4. Negative 1 times itself is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And so if I wanted to graph, if I knew that what this function looked like, and I wanted to graph x minus 2 squared, notice that the minus 2 happens before you square it. It's on the inside. So this is our horizontal left-right shift. This is going to shift us right 2 spaces. The minus 3 happens after. So after you've already made this figure, now we're going to shift down 3 spaces. So what I like to do, just in terms of like getting a quick one here, we're going to go to the right 2 spaces and down 3 spaces. That's where our new vertex is going to be. From here, all I need for today, I could do that for all the points I know. I just need a quick sketch. I just want a quick sketch of what this looks like. Like I have a general idea of that this x minus 2 has shifted me to the right 2 spaces, and the minus 3 has shifted me down 3 spaces. That's plenty. Second kind of function we could have a cubic function. Instead of times itself, and times itself again. So there's 3 of them. So negative 2 cubed. This one, I'll take a second to pause here just to show you what that means. That means negative 2 times negative 2 times negative 2. We do it one at a time. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. That's why negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 1. 1 times 1 times 1 is 1. 2 times 2 times 2 is positive 8. So that's your cubic function. We'll work on it, but what I want you to focus on is this plus 5 and then this plus 2. Think about what those are going to do to this function. The plus 5 means that now x has to be negative 5 to get a 0 on the inside of that cubic function. It's the inside, so that's going to shift us left 5 spaces. And then the plus 2 is going to shift us up 2 spaces. So I'm going to take this function. I always just like to think about the key point here. It's not technically a vertex, but it's that key value, that 0 value. We're going to go over 5 spaces to the left and up 2, and that's going to be the new sort of center of our function, that key point that draws your mind to it. I'll put these just like the other function has. I'll put this one just like the other function has. Again, just kind of eyeballing it here. Today, roughly your cubic function is going to look like that. It's the same function, just left 5 spaces and up 2. Now we've also got the opposite of cubic and quadratic. The opposite of quadratic, what if instead of squaring the function, we took the square root? So the square root of 0 is 0, meaning what number times itself is 0? 0. What number times itself is 1? This should say square root here. 1. What number times itself is 4? 2. What number times itself is 9? 3. So that's where those square roots are coming from. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. That's where that's coming from. Important part for today is that you see this x plus 2 on the inside, and I want you to think left 2. Because now instead of x of 0 giving us 0, we need that x to be negative 2. So we're going to shift. The first shift we're going to do is left 2 spaces. But we're not done. We also have a shift of down 1. Our new vertex is going to be right there. This one I'm just going to do a super quick sketch. It's the same function, just everywhere shifted left 2 and down 1 space. That's your square root function. The last one, and kind of the coolest one, cube root. This means what number times itself and then times itself again is x. So the opposite of cubing. So what number times itself and times itself again is -8, -2. Cube root of -1, -1. Cube root of 0, 0. Cube root of 1, 1. Cube root of 8, 2. Again, because 2 times 2 times 2 equals 8. All I need you to know today, though, is that if we had a -3 on the inside, that would mean we are moving right 3 spaces, and a +4 on the outside, that would mean we are moving up 4 spaces. So we're going to go to this critical value here. We're going to go right 3 spaces. We're going to go up 4 spaces. And we're going to try and just loosely today replicate that same looking figure, but with a shift of right 3 and up 4 spaces.